Well, we are back, I guess. Let me check the sound first. Hopefully it works. Come on. Come on. I need to check my YouTube channel, of course. Does it not want to start? Maybe. It did start. It also did like the the old thumbnail. Let me check the sound. Does it not want to start? Maybe. Okay, it's fine, I guess. It's not very loud, but it works. I mean, not that anyone is gonna watch it, but fair enough. Okay, let's continue from where we left it with return oriented programming. I kinda like took a small peek on these, not a very big one because I was like, fuck, I should do it there. But let's keep going. The basic of return oriented programming is stringing together small chunks of code already present. Yeah, passes parameter that already okay. Libc's library. Libc. Let me be sure. Standard library. Okay, and glibc is the GNU C library. System essentially allows us to execute some commands like cat, binsh, echo, etc. If you can find the location of the commands, like such as cat flag, and then pass it as the parameter to the system, it will execute the command and return the output. Yep, a more advanced series is the binsh, which essentially gives us a terminal access. A shell, yeah, basically. Doing this is not simple. Yep, fair. It needs it's complex. To be able to properly call functions, we need to have to understand how to pass parameters to them. So let's start with calling conventions. Let's download it. Download, I said. Nice. I want to check something before, although it kind of worked, not fully. Move from downloads. Convention, call a convention zip to here. Let's rm maybe the source, the solve, and the vuln. Nice. Also remove the cell, and let's unzip the calling. So comparedly, oh shit. We have source and two executables, vuln32 and vuln64. The vuln32 is the 32-bit the ELF 32-bit executable, and the 64 is the 64 the 64 what's the word? I remember the English word. Anyways, so essentially this is the 32 and this is the 64th bit. Okay, let's cut the source, and we can see again a couple things. We can see the beginning, how it's called. The only difference is like this has minus M32 to convert to a 32 bit, and this is like a 64. You might be asking why the 32 and not the 64. This is more a historic thing. All computers have the 32, but not all have the 64 bits, and that's why it still exists. I think it's backwards compatibility, if I'm not wrong. And we call the vuln function with one parameter. If it is 0xdeadbeef, it says nice, and if it's not, it says not nice. If we execute both of them, we will probably see it. Yep, it's the exact same output. Now, let's actually, before we see in the tutorial, I will try to check it out on my own with you. from your house where you're probably watching, or maybe not, you are not here. Info functions, to see the functions, we see main vuln. If we disassemble the main, initialize this stack, and here it adds this to the EX register. The stack pointer gets the 0xc, and we push this value to the stack in order for it to be like be passed as a parameter to the vuln function. Then we add some space, we subtract the space, some space. Don't really remember why we do that. Essentially, like we add like 10 bytes and then we subtract 0x, which is 13, 12 or 13. 0x9, then it is AB, so it's probably 12. Let's see, 0x, it's 12, yeah. Let's disassemble the vuln. Essentially, it just creates some space for the functions to be called, and it gives them this parameter for this one and this parameter for this one. If we disassemble the vuln, as I said, here again initialize the stack, and it compares the base pointer plus 0x8 with 0x_deadbeef. Essentially, in the since we post this into this this stack, this is from the previous live stream. Okay, so this is the stack, and inside the stack, in here we push this value. So we have 0x_deadbeef, if you can see it, 0x_deadbeef, and in here it compares these points to the base pointer, which is probably around here. This is the base pointer, and like the stack pointer is gonna be around here. So if we like subtract, does it subscribe? No, it adds 8. So if we add 8 to this, it essentially will go down to this, and it will compare this value that exists here with 0x_deadbeef. And if it is not equal, it will jump to plus 48, which is just right here, and it will load the effective memory of this and create some space, and put the method not nice, which exists right here. If I think if we do x dash s, it's probably no. What was it? Was this x dash? No, I don't remember. Anyways, it essentially, this is like the else, and if it is equal, it will continue from here, and it will call this, and then it will print the message nice, and then it will jump to 68, which is the no operation in which it returns. Essentially, this is the one if, and this is the second if. That's it. Like in the first occasion, it will pass this, and in the second occasion, it will pass 0 dead code, 0x_dead code, and it will essentially like it compares this, the 0x code, with the 0x_deadbeef, and it's gonna be, is it equal? No, since it's not equal, jump to here, to this. And that's it. Let me check if it says something else. We run, oh yeah, this is for the 32-bit, and if we actually like bin main, and then I will actually break and wait at here, just before the comparison. If we run it and see, we are right here. This is where the first argument is, and we can see that in the base pointer it is 0x_bif minus 0x_bif, which equals 0, and since it does equal 0, it will continue, and it will load the effective memory of this, which has this. Oh, it's this. This is probably exast s. Come on. Not here. Here. Cannot access memory. What? This. Okay, let's step forward. Compares. Step forward, and step forward. Now what is the EX value? What about now? Now it has the value, nice. Where is this value saved though? It doesn't say. It just like it saves it after, and we can see that its value is here. And then if we continue, this is for the second one, for the second call. It printed nice for the first one. And for the second call, it compares 0x.code minus 0x.bif, and it's not equal, so it will do the jump, and it will go to plus 48, which will print the note nice, as stated. If you like want to see the visual, essentially this will just be equal to like 495, which is not 0. And that's it for the 32-bit version. The 64 is kind of different. If we this as main, this and this as vol, you will see that compared to before, this has E and now it has R. It is to say that this is like 64-bit, and essentially the E just means that it's the lower 32 bits. So like as 64, this is a 64 bit, consists of two 32 bits. This is the high 32-bit and this is the low 32-bit. And here in the low 32 are the EDI, EXI, etc. And essentially this can like keep going like to 16, which is like I think the DI, and then it is the or A8, or it's something like that. 64-bit to 32-bit to 16-bit. I think there is like a picture. Registers. The 64 is with the row, this is with the E, and this is like without any of them, the 32 bits. And he analyzes it, assembles it. If we look closely, we see a pattern. Calls it. Yeah, like I said, it pushes it into the stack first. We literally push the parameter to the stack before calling the function. Let's break it down. Oh, he like looks at the values. Okay, let's try to look at the values. B main and B at vol plus, how much was it? 12. Let's run it, continue, and let's look at the extras S, I think, or XSI 20i, the values of ESP. Not I. Is it S? No. Definitely not S. Is it X? Yeah, it is over X. And we can see that it is 0x dead beef. for the first one. And if we continue and we hit the second one, now it should be 0x dead code. Like this is the last thing on the stack. This is like the top of the stack. Will it repose it? Yep. The first value here, there is the return pointer. Somewhere here. Maybe. 0x8. 0x8. 0491. Yes, it's this. This is the return. If we do it like 40, would it change? Will we be able to see the dead biff? No, let's do 50. No, I don't like when it does that. No, let's run it again. Let's continue and let's try it now. This is the dead beef, and I don't see the other one. It's probably gonna be like after. This makes sense because the return, yeah, so it should be on the top of the stack. Now let's assemble sim vuln. And here I'm showing the full output, and yeah, it essentially compares it with the 0x dead beef, and then it returns. And then there's the 64. This as vuln, and it just like the same thing. It compares it the base pointer minus 0x4 to the dead beef, because this is like 4 bytes, 1, 2, 3, and 4, and it's that simple. He says the difference between like it has RDI and EDI. Oh yeah. For anyone wondering, I did knew it before I read it. If you did. Is there anyone actually? Nope. Just me, myself, and I. I like it. It's kind of chill. And that's it. There's nothing more of this. And there's another one with multiple parameters. Essentially, it will check if like all the parameters are correct. Let's try it because why not? rmall move from downloads, calling here, and unzip it and cut it. We can see it's the same thing that is here. And let's use spawn debug -q vuln32 info functions classic this as main. We see that they are posted to the stack before it is called. Like firstly it starts from the last one and then it goes to the first one. If you like say it goes like first the code dot, then the dead code, and then the dead beef. I don't really know why. Oh, if you actually think about it, does make sense. I'm just like a little stupid right now. It's like the night. So essentially, let's delete everything. Like I said, the last thing that we can pop is from the top. So it will, on the bottom of the stack, it's gonna be the last one, 0x code dot. Then the 0x dead code. And then the 0x dead beef. And because it's a stack, we like we read from the top, so that's why it is in the reverse. Pretty simple. I'm like slow sometimes. Yeah, it compares them like from the stack. The first one is the dead beef, then the code, and then the code dead. If you actually see, the difference between those two are all 4 bytes. If you don't believe me, I will show you. 0xc minus 0x8 is 4, and 0xc, if you are wondering, the hex of 4 is 0x4, and 0x10 minus 0xc is again 4. So they're exactly 4 bytes because their length is 4 bytes, because it's 1, 2, 3, and 4. And again, this is the if. Compares them, and if all of them are correct, then it continues. If not, it jumps to here. Where does it jump? To 66. It jumps to here and continues. If everything is correct, it continues normally until it goes here, and then it will jump to here. Yeah, that's pretty simple. That's the most of it. Let's run it. Let's break the main and break out vuln right before this. Plus 12. Let's run it, continue, and let's do x task 20x ESP. Let's see the values. It is 0x code, the code DOD, the dead code, and dead beef. And we will see that they're compared like equally, like first one is dead beef, this, then this, and then this. And if we step like from each instruction, we can see that the comparisons are correct, and it prints the nice. And if we continue again and we search it again, we see that only one of them is correct and it will fail. Am I right? What was the code? Yeah, it is 1, 2, 3, 4 and A, B, C, D, F, 10. Yeah, it is exactly correct, and we will see that it will fail on the first one and it will print not nice. If it fell like either in any of them, it will still like jump here. The 64-bit is essentially the same thing, just with RDX, RSI. And he wants to make a point that because here in our code, not in our code, in the assembly, let's disas full. It has the EBX, ESX. This actually disas main, because it has the E in front. Or was it the other one? Oh, this is the 32. Wait, I meant in the 64. This main. He wanted to make a point that those might be like with an E, but you can actually make them like all this, and it will just be converted to RSI, RDI, and etc. And this is what you want to point out. Now we are going into gadgets. Well, be prepared for the flashbang, because it is much easier to see them. Okay, so gadgets are small snippets of code followed by a return instruction. This is purely for the 64-bit. In 32-bit you can call it without this, but in the 64-bit you can't. You need like to pop the registers. And he said that gadgets are small snippets of code followed by the return instruction, e.g. pop RDI return. I will show it to you like after I finish reading it. We can manipulate the return of this gadget in such a way as to string together a large change of them to do what we want. Let's for a minute pretend the stack looks like this during the execution of pop RDI gadget. So this is a stack pointer. What happens fairly obvious. We popped RDI. So this is the RDI. DI is like the destination index. SP is for stack pointer. They have like a meaning. It gets popped into the destination index as it is at the top of the stack. So since it is at the top, then it will be popped and the RSP will go to the previous one or to the next one, like the one below. During the pop RDI, once the pop occurs, RSP moves and it is on the second one. And since return is equivalent to pop the instruction pointer to 0x this, it gets moved into the instruction pointer. Instruction pointer tells the computer, the CPU anyways, on what command it wants it to execute. It wants like to move to this location, like it wants to point to 0x to this memory location. So the problem is if we manipulate this and we can do what we did in the beginning and redirect everything. Utilizing gadgets. When we override the return pointer, we override the value pointer by RSP. Once the value is popped, it points at the next value at the stack. But wait, we can override the next value in the stack. Yeah. Just to point out, if I say something and you don't understand it, please comment on it. I will either, if it's complex, I will make a video about it. If it's simple, I will probably reply in a comment. Let's say that we want to exploit a binary, jumps to pop RDI return, and it pops 100 to the RDI and then jumps to the flag. Let's step by step. Okay. When I first read it, I didn't understand it, and I still don't really understand it completely. So essentially, in the stack pointer, it points to this, the gadget address. And the instruction pointer points at the return address. On the original return, which we override the return pointer, we pop the gadget address in. I don't know how we did that. Let's pretend that we did that. Now the instruction pointer moves to the point to the gadget. Moves to point to the gadget. So this will point, the instruction pointer will point to the gadget that we want. And the stack pointer moves to the next memory, so it will move to 0x100. Stack pointer moves 0x100 and the instruction pointer to the pop RDI. Still don't really understand how that worked. Now when we pop 0x100, it gets moved into the RDI. So this will be moved to the RDI. Not here, to the destination index. So this will be popped and the RSP will go to the flag. And because here it says pop RDI, because this was in the RDI and we remove it, because this is a stack, it will go to the return. So it will return the flag. I'm on the point that I don't understand it. Like, I get it, but I don't really get it. Essentially, if the gadget pops value from the stack, simply place those values afterwards, including the pop RDI in return. If we want to pop 0x10 into the destination index and then jump to 0x16, your payload would look like this. The gadget address will be pop... Oh yeah, the gadget, I forgot about that. Okay, let me show it right now. I used to use a tool called Roper. However, I cannot use it right now. It needs to be installed with pip, and I tried to do it, pip install Roper, to break the system packages, and I'm getting this error message, which is some meta generation. And I didn't want to deal with that. I tried and didn't figure it out. I spent like 1 hour. So the next thing is rope gadgets, which seems straightforward, which is way easier, and we can do minus minus binary, the vol 64, and we can see a lot of operations and their addresses as well. So for example, if we want to, we can grab the pop, let's do it, pop RDI. What was it? The pop RDI? It was pop RDI. We can essentially grab it, and we can see it was in this address. If we go to this address in here, FB, we can see it right here. It has also the base pointer, destination, the source, and you can essentially use it to do this, this weird thing. So popRDI returned the address. So this is the address that we want. And then the value that will be on the destination is going to be 0x10, and the instruction pointer will get the value 0x16. If you have multiple pop instructions, you can just add more values. He's saying that sometimes you will not get like RDI alone. Like if you do like pop RBP, you can see that there are a couple of cases. There is one that it's alone, and there is some that it has some extra registers. If this is the case, you need to fill those extra registers. Otherwise, it will override them. Like if you override like by 4 bytes, the 4 bytes will just go to the next register and not the return address. So be careful with that. We use destination as an example. If you remember, that's the register for the first parameter. Yeah, this means control the register using the gadget important. We're gonna use, yeah, this, I took it from him, this one in particular. I used to use Roper. It is this, I was stuck with it. Essentially it says like download this, and this, and then you can download it using pip install Roper. And it didn't work for me, and I'm tired and I don't want to deal with it right now. So let's move on. This will be like a small exercise where we will try to pop it. I will try to not say it because I have not seen the solution, because I want to try it myself, at least for the beginning. I will like 99% sure that I will probably fail, and I will need to do it. RMall, move from downloads, what was its name? Exploit, to here, and unzip it. So let's cut the source. So simply char, and we can call the flag, and if the values are 0x code and code dead, it will work. Okay, so let's create, I will first do it with 32, and then I will try the 64. Nanosolve.py from pon import all p is equal process dot backslash vol, and our payload is gonna be what is it gonna be? So overflow it by 40, a times 40. Let me actually run it. Pon debug-q vol 32. Cyclic 100 r, and this cyclic dash l, so it's 52 again. And next I will call the flag info functions. Oh, it's gonna be like the load, I need to restart. Info functions. This is gonna be the flag, And then we will need to add the values. Clear, clear. Actually, let me try to do it from this. This as main. It's not this. This as flag. So the first one is gonna be this. So this should be the last and this should be the first. P32 this. Not that. And payload plus equals I said. P32 and 0x dead code. And Peter dot send line, not this, payload. I will try the bit dot receive all. They receive 496. It might work, it might not. If it doesn't, then we'll move on with our lives. Python 3 solve. Oh yeah, it is the 32. It didn't work. Does anyone watch? Nope. Okay. So let's show some info. Context. What was it? I don't remember exactly. Not this, not this. It was in here. Context dot binary is equal to debug. Yeah, let's just do like this. Log.info p.clean send line, and it's not gonna be interactive though. So it is log.info and p.clean again. Okay. Maybe this works now. Overflow me? Nope. I wanna watch the payload itself. Let's do the sit. Pawn tools sit. No, it's fine. Definitely not. Okay, this is it. What about now? Okay. So it did send them. I don't think it even crashed. I sent it 41 bytes. What? How does that make sense? It's R1. Okay, let's do it faster. Python 3. Print A times 52 plus B times 4. And yeah, it is correct. How does it not work though? Do I need to put it before? No, I need the payload to be first the address and then them, I think. Should first in the at the top of this. No, I did them in the wrong order. This should be at the bottom. Oh, yeah, this is annoying. If you are wondering why this is happening, I have no idea myself. If I press it like for 2 seconds, it just goes way too much. It goes more than I want. So I have to tap it. I don't know if there is a solution. Okay, what about now? I guess it's this and then the address, and it didn't print it. Send line payload, this should all be correct. Don't understand why it's not. Log.info. Okay, what is the issue? I don't understand. Why is it sending way less than it should? One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20. Only 20 plus mine. Why? If I remove the P, it's gonna throw an error. Yeah. So I need to put this. Maybe I need to like 240. No. Send 0x. Oh, it was in 0x. That's why. X 52. It says 0x41, which is probably 52, 60. Python 3. 65. Okay, close enough. Let me think. Still a year, still no bitches. Okay. So let's see what I'm doing and what was wrong. So I'm sending 52 bytes. Okay. Then after the first 52, it's gonna overwrite. I want first the top of the stack should be the address. So it should be the last. Then the second and then the first. Okay. I don't see the issue. What am I doing wrong? Let me like write it in Python. Python 3 does C. Oh yeah. Does E. Wait. Man Python. Does B does ignore not E. I think there was a command, not sure. Okay. Let's check his let's check his out, see where it's different. What? Okay, so I had it almost correct. So this was the initial. Okay. And then it adds a return. So payload plus equals P32 0x0 1. It still didn't work. What? Okay, let's remove it. Let's copy exactly his. What? Okay, so instead of that, I had. Oh, shoot. I had it the other way around, I think. I think I had this first. Yeah, and this second, it was the other way around. That's why it didn't work. So you need. Oh, it's in 64 bits. I'm dumb. Okay. So let's do the solve 2.py. From pawn import all p is equal process dot slash vol 64 payload. Okay, let's do the pawn debug again, but with the 64 version. This as main, this as flag. Let's run it. Cycle 100 R, and it's this. Which is this? Does it understand it? Select that cell. This. Which is this? Which is 56. Okay, so payload is gonna be B of A times 56, and then the payload is gonna be. Oh, it's gonna be different. So let's firstly call this P64. This, I think at least. This, yeah, I will not say for now, and it will be on the beginning, the address probably, and I did not like in my mind it made sense. Payload plus equals P64 what? This one. And payload plus equals P64 and this. Okay. We will probably need to pop the SI. or where is gonna be saved? It's gonna be SI or ADI. Probably ADI. So let's do rob gadget and room 64 binary. I forgot about that. And it happened again. Nice. And I should grep the pop RDI or no EDI. There is no EDI. Oh yeah, between here. No EDI, so it's RDI and it's this address. Is it before? Think so. Plus equal P64. This. And I need to do it for both. Pop RDI. I will probably do it for both, I think so. If it doesn't, I will try it. If it's wrong, then log dot info p dot clean p dot send line payload and log dot info p dot clean. Again, solve 2. No. Okay, let's try it like, let's try it with a second one. And still no. Okay, so let's search 64-bit. 64-bit. What was it? Gadget. Rob gadget. I just want to know like I really don't remember like the another orientation, the row, how they are put, like the correct order. Yeah. Order of 64-bit rob gadget. I don't remember it, and I'm actually saying it, so I don't know if it makes sense. Yes. I want to pop, yeah, the RDI, I'm doing it. So what, let's check what I'm doing. This is the initial address. Then I pop the RDI, I give it this address. Or is it reverse? Huh. Should I try it? Sure. Let's try it in reverse. So I'm deleting this. be a lot. Okay, log.inf, that's fine, that's a little more than I wanted, but it's fine. Oh shit, I should have copy and pasted. It's fine. Payload plus equals P64 and it was 0x dead code, I think. 0x dead code, yes. Nope. Okay, what am I doing wrong? I have seen a video. Same logic, except we have to utilize the gadget yes to fill in the request. In this case, we have to fill it before the function is called. Oh. Okay, so before this happens, so we need to do this. So let's. Can I cut it? Split, paste, close, or close, cut. Not what I wanted. Control Z. No, how was it? Control. It was from pawn import all, and I will paste just here, and I will do bam, 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 bam. Oh fuck! And I accidentally overdid it. Well. Okay. Here, here, and then this one. Payload plus equals P64. What about now? Still no. Okay. So is it now reverse? Okay. Oh no. Okay. And before this, and no. Okay. What is it? Pop RDI, pop RSI. What? Okay, I am popping the RDI. The RDI value is this, which is correct. Okay, so correct, correct, correct. Y. And it adds payload plus equals P64 0x0. And then is the address of the flag and then again a 0. Why again the 0 after? I'm kind of getting confused with the zeros. P64 0x0. What about now? Still no. It wants value not important, and this is probably the same as this. Return address, don't care if it crashes when done. So I'm wondering why the it is the RSI. One of them is this destination, one of them is the source. So rob gadget minus binary vol 64, and I need to grep pop RSI, which has this value. Is it the same as him? Yep. Oh, yeah, this is because we have like pop R15, we need to add this because we don't want to actually pop this. So it makes sense in this occasion, yes. In this occasion it makes sense, but why do we need like the RD and the RSA first? Let me actually call the classic not Gemini y in rope binary exploitation in 64 bits. Do I need pop RDI and pop RSI instead of only pop RDI? Maybe. Okay, the short answer uses past argument to function. Pop RDI only allows to control the first argument. Oh, that's why. Since this is the EDI and this is the ESI, that's why. I thought this would cover both, but it didn't. And if it has like 3 arguments, it will be like another register, like maybe R15. So bullshit. Okay, let's do like until the stack alignment, because let me change also to black mode. I'm getting kinda distressed and tired. How long has it been? It's been 1 hour. Damn. When was it? Like an hour? Okay, let's open it. Close. Clear. RMall. Clear. Move from downloads. What's return? Return to lib to here. Okay. Return to libc, as we said before, it is the standard cell library, which has some extra functions, like it has some system calls and some other things, and zip return from here and out. I have not like read it. Okay, the return to lib is a base of system function found within the C library. This function executes anything passed onto it, making the best target. Another thing found is the bin sh, which gives like terminal. You pass the string to system, which will pop a cell, and that is the entire basis of it. Passing bin sh as a parameter to system doesn't sound too bad, right? And it's gonna be hell upon earth, I'm sure. So disabling it is the first step. Clear. Manual exploitation, getting libc and its base. Fortunately, Linux has a command called ldd man ldd prints shared object dependencies. Prints the shared object, shared libraries required by each program or shared object specified on the command line. An example of its use and outputs the following: ldd bin ls will print the shared libraries of the ls command. So we do ldd ls cat. What? Where is cat? User bin cat. So ldd / user bin cat. And we see some information about it. This probably works for ls and s8 as well. Yep, it works for all of them. We need lib6, so ldd Vol 32. It is this as stated. We need yes. So the base address of libc is this. Just this. Wait, it's different. For me, those two are different. To him, it's the same. No, it's not actually. It's this. This is a D and this is a C, so it's not the same. libc base and system and this offer may be different for you. This is a problem. It just means you have to different. Yeah, make sure to use your values. Getting the location of system. Read elf. Read elf is like to read the elf. The elf executable libc.so.6 and grep system. No, okay. What files are in here though? Wait, can I even run it? So vol32. Yeah. Wait. cd slash bin 32. No, cd slash bin 32. Or just cd slash bin ls. Grep libc. ls grep libc. Is it not? .so.6. What? lib32. I don't have the libs. Yeah, it's right here. So it is in lib32, not in bin32. I'm dumb. It says I'm fucking dumb. Oh my god, I cannot even see clearly. lib32. Yep. Then we need to use the readelf command for this. The s flag tells readelf to search for symbols, for example, functions. Here we can find the offset of the from libc base is 0x, so it's this. So it's this for me. Stop watch. Stop it. Get some help. Getting the location of bin sh. Since bin sh is just string, we can use strings dash a dash tx lib32 libc.so.6 grep bin sh, and it's just this. A tells it to scan the entire file, and tx tells it to output the offset of hex. Pretty important. And then there is the exploit. Okay, let's try it on my own, which who would expect that I wouldn't do it. Solve.py from pawn import all p is equal process of vol32 What else? Payload is gonna be equal to B. Okay, I don't wanna lose this. Okay, let's actually save it before I do anything. The system is gonna be this, and the bin assets is this. Okay, so we can now clear upon debug dash q vol 32 cyclic 100 r. It is tua cyclic that's L. Tua 76 times 76. And let's have not actually seen the code. This as main. Again, it calls the vol, this as vol, and it will put the overflow and it will get something. There is probably nothing else here. It's just, this is like the lesson. Yep. And okay, let's see it. Our payload plus equals this system, and then the BNSA, it's P32 system, and payload plus equals P32 BNSH P dot send. Okay, so log dot inf. No, it was P dot clean. Or was it log dot info P dot clean. Dot send payload and p dot interactive, because we will gain cell, and Python tree solve. Okay, let's remember it has 3. Bro, it's just just 0x 1 2 3, and this is 0x this. But now wrong file. Oh, I got it off. I was like excited for 1 second that I succeeded. I was like, nah, no way. What if I remove this? Of course I get it off after this. Yeah. Why though? Dot send Maybe send line. Don't think it's gonna solve it, but I'm not losing anything. Still got elf. What is the name of elf? Cross. Jesus. Elf encoding. Conditional computer persistent. The number of data that can be. Yeah. And the file. Oh, I forgot. I forgot the lib base. Libc base is gonna be. Oh, what was it? It's not the system. It is. Which one was the libc base? It was for the program. LTD this. So it is this. So it is this. So I'm gonna do this libc base plus this libc base plus this. And now still getting an elf. So if I add like a 0 here, it's gonna change. P32 0x less. Bruh. Why? Why does it need this 0 inside? Let me ask the AI cat sol.py. Again, I was close, but well, as they say, I tried too hard and got so far, but in the end, it doesn't even matter. Still didn't get the 0. Fake return address. The function system itself, one system should go after it finishes. Oh, that's why. Because we need to. We actually said before, you need to, for the system address to like return to something, and it will return to like 0x0, and so that it will not overwrite this. So essentially what it did in my program, it overrode the return address with binsh. And now it works. Nice. Okay, the 64. I will try the 64 again. Maybe I will have some better luck. So from pawn import all, p is equal process vol 64. Payload is equal b of a times pawn debug dash q vol 64. The dash q is to make it quiet. Cyclic 100 r and cyclic dash l this, so 72. So let's start slowly. This is... Oh, I need the values again. Okay, save. Oh shit. Oh no. I accidentally closed it. Oh shit. It's open. Okay, that's fine. Okay, cat solve .py. Oh, cool. Okay. Okay, from... No, actually. Let's move the solve to solve .py. And after this we're gonna do payload plus equals. In the previous one, did we first pop it? No, first... Yeah, we first popped it. Okay. So this as full RDI. I will pop the RDI. So in rob gadget minus binary vol 64 and grep pop RDI. Forgetting that. Okay. What? Nice. It's gonna be to P64 this. Then our payload is gonna be plus equal P64 the system. Then the payload plus equal P64 0x0. Then the payload is gonna be plus equal P64 the bin sh, and then we do p dot send payload and p dot interactive. Oh, Python 2 solve 2.py. Okay, I'm getting an eye off. Where did I make a mistake? Oh, LDD vol 64. This is the big mistake. Nope. This should stay the same. Do I need to pop it here again? The RSI. Pop RDI. Oh, it's a reverse. It's this. No? Okay, what else? Those are the same, right? Yes. Oh, no. System is different. It's... okay. Not here. I will just do it here. instead of BNSH, come on, it's gonna be the regular one. Or libs64. lib64. Oh. CD X 86. And I will do LDD the libc.so. This one, and which one is it? Hopefully this one. This is the SH one, right? Oh, is it the libc base? And let's do what was it before one? It was here. And I should do strings. Does A, does the X, and libc.so .6 grep bin sage. System. What are those? What are those? Ah, yeah, it's not exactly, it's this. Read elf das s libc.so .6 grep system. It's this. So now, does it work? Nope. Oh, LD vuln 64. This is wrong. Now it might work. Nope. So this is correct. This is the system. This is this, and pop property is the same. How it sensed it. Yep. Then it's been system 0. It's p clean. Send line on p clean. P dot clean and p dot send line. Still nope. Oh, this is so much fun. Okay, let's do it again. So, oh, it's this. I want too fast. Nope. Okay, let's do the this, but it's gonna be on lib and 86. Where is it? 80x x 86. Yes. Okay. 0x binus 8 0x 1d c4 c3. Yep. And this same thing. x86 0x. Yes. Oh shit, it's this one. 5c. It's correct, but it's not working. Hmm. 0x. Okay. Pop. RDI is this. Binus 8. Yes. So I'm utterly in a what the fuck. Okay. Let's try the one that he's saying here for the third with the automation. And I don't know if I will do this. How big is it? That's what she said. Let's do it like nano automate.py from pawn import all health is equals context binary is equal elf from 32 p is equal to the process libc is equal f dot libc libc dot address is equal what was the base address? It's this. And what else? System is equal to libc dot sim system. So essentially, instead of us doing it, it will do it itself. Binsh equal to next libc dot search. What does it need this the next? I don't know. Binsh. I'm bored to do it. I'm gonna just copy and paste this. It's the same thing. And Python 3 automate. And it works. So the difference is that instead of us going to search like all of this The rest you just need to find the base address and it will locate it by itself. Stack alignment. Oh, okay, it's pretty small. So no, it's actually perfect size. It's huge. Oh my god, how will everyone take? A small issue you may get when pawning on 64 bits is that your exploit works perfectly locally but fails remotely. Fair enough. This is probably mostly on CTFs, or even fails when you try to use the provided libc version rather than your local one. This arises due to something called stack alignment. Yep. Essentially, okay, that was an accident. Essentially, the 0x64 guarantees 60-bit alignment on a call instruction. libc takes advantage of this and uses SSC data transfer instruction to optimize execution. System in particular uses tricks such as move ups. That means that if a stack is not 60, if it's not 16 bytes aligned, that is RSP is not multiple of 16, the rope chain will fail on system. To fix this in your rope chain before you call system, place a singular return gadget. Oh, that's pretty easy. Okay, that's pretty easy actually. If you don't understand and want to explain it simpler, if it's not 16 bytes, a multiple of 16 bytes, if it's example 18, it will like go up to 32 to fill in the gap and like align the stack itself. That's it. Nah, tomorrow. Thank you everyone for watching. Probably me myself and